Hi, everyone. In this video, we're going to take a look at our first chapter of the course. And this one really focuses on just some basic vocab related to statistics in general. We have to understand the basic verbiage that goes along with the content before we can really get into the nuts and bolts and really start to get our hands on some real statistics. So let's jump in. So, statistics is the science of conducting studies to collect, organize, summarize, analyze, and draw conclusions from data. A variable is a characteristic or attribute that can assume different values. So, lots of different variables can be used. We're going to look at tons of them throughout the semester, but basically, a variable is anything that we can go out and collect data from. And data are the values. They could be measurements or observations, depending on what kind of variable we're working with. But they are values that the variables can assume. So, for example, if my variable is height, then the actual values of height would be those data. A random variable is a variable whose values are determined by chance, like the value of a roll of dice. So the first example of variable I gave was height. That's not something that's determined by chance. Everyone has a specific height at a moment in time when you would go out and collect their height. It's not like you would walk up to somebody and their height would then be randomly determined before you measure it. They already have an existing height, so it's not a random variable. But if you took out a set of dice and rolled them, the value that they came up would be determined by random chance. A data set is then the collection of a bunch of data values. So if you go out and measure the heights of 50 people, all their values put together, we refer to those as a data set. Each individual value in the data set is called a data value or a datum. So there's nothing super crazy here. A lot of this stuff you guys have heard before and worked with, but we just want to have our vocab correct so that when we're discussing it together, we're all using the proper terms and no one's confused by anything that's thrown out there. So there are two branches of statistic, descriptive and inferential. The course itself is actually split up between these two. So the first half is mainly looking at descriptive statistics. So descriptive statistics consists of the collection, organization, summarization, and presentation of data. So we just go out and look at what is now or what was before in the past, and we organize that information, summarize it, find the really important pieces, and then we present that to people. It's the goal of the statistician simply to describe a situation. So, for example, every 10 years, the U.S. Census Bureau conducts a massive survey of the U.S. population. They collect information on average age, income, and other characteristics of Americans. Then they have to organize and summarize that. The country spends billions of dollars. Federal government spends a lot of money collecting this information so that they have an accurate account of vital information for the entire population of the country. So they'll present it in data charts, graphs, tables, whole bunch of different ways to organize it, but they're using descriptive statistics through that process. The other side of that, inferential statistics, consists of generalizing from samples to populations, performing estimations and hypothesis tests, determining relationships among variables, and making predictions. So really the way this course is going to work is we're going to learn how to do all the descriptive statistics stuff and get the foundation for our statistical understanding and reasoning. And then we're going to transition into making these predictions. So the biggest thing with inferential statistics is being able to generalize information that you collect from a sample to or about a larger population. So the population is the larger group. It consists of all the subjects, whether they're human or otherwise, that are being studied. A lot of times a population is the group of people you want to know something about, but because of time constraints, lack of resources, lack of money or time, you just can't simply go out and get enough information from everybody. For example, the Census Bureau, like I said, costs the federal government billions and billions of dollars to collect all that information. That's why they can only afford to do it every 10 years. If it was really easy to get information from the entire population, then they would be doing it every year as opposed to every decade. So instead of collecting data or information from everyone in the population, a lot of time what we do is we'll select a small group of subjects from the population who, if we design it correctly, does the best possible job of representing everyone in the population, and that is our sample. There's different methods of collecting or choosing that sample, and we'll look at those a little later on. But the idea is if we do a good job picking that group, then the results that we see in our sample will be able to use those or use those people and their data, their values, and their results to make predictions about what we would see if we could get data from everyone in the population. So, for example, a researcher may wish to know if a new drug will reduce the number of heart attacks in men over 70 years of age. Two groups of men would be chosen. One's given the drug and the other a placebo. Then the number of heart attacks in each group would be counted. A test would be ran and the results analyzed. So, again, the idea here is we're trying to look at information for this small sample to see if this new drug would seem, if it would seem likely that this new drug would yield really good results for everybody in the population. So that's the big idea behind inferential statistics, taking information or data collected from a sample and trying to use it to predict things or test things about the larger population. So there are lots of different types of variables, different ways to categorize them. So the kind of information we can collect from members of a population or sample can be described and classified in several different ways. First, we could work with qualitative variables. So these are variables that can be placed into distinct categories according to some characteristic or attribute. So the big key word there is categories. Think of different categories. So if I asked you for your favorite of something, then that's most likely a categorical or qualitative variable. So some examples here would be gender, month, color, state, country. So those would all be things that I would have to list the possible choices, and then you'd have to check off a box or pick one of those. Qualitative variables can then be broken up into nominal or ordinal data. So these are two kinds of qualitative variables. And we'll get into that a little bit more later on. The second kind of overall kind of variable is a quantitative variable. So rather than categories, these are numerical in nature, and these values or these variables can be ordered or ranked. So quantitative always have to be numbers, but then they also have to be numbers that can be quantified or compared based on their size. So the big exception here is any kind of number that doesn't really correspond to a size of something. So the go-to example for this would be a zip code. Everybody who has an address has a zip code, and that zip code is always numerical, but zip codes actually refer to geographic locations. So they actually fall under qualitative variables. So anything else like that, your house number, your phone number, your license number, your license plate number, all of those things could be numerical, and most of them are always numerical, but they don't really correspond to things that can be ordered or ranked, so therefore they fall under qualitative. Quantitative variables, some good examples here would be age, weight, height, salary, or time. So those are always numeric, and all of those different values you can order who makes more money or who is taller or who weighs more. There are two types of quantitative variables, and it depends on what kind of numbers we're working with. First, discrete variables assume values that can be counted, and they take on integer values. So there's gaps between the possible choices there. So, for example, the number of children in a family, whole number values or integer values. You can't have 2.5 kids. The other side of that, the other kind, are continuous variables. These can assume an infinite number of values between any two specific values. So if you think about your variable, whatever your minimum value and your maximum value are, then you would be able to have any number that falls in between those two be a value that you collect. So these are obtained usually by measuring and often include fractions and decimals. So it's not always a necessity that they could be or that they have to be measured. If you think about, for example, salary could be a decimal. It could be anything between 0 and the most amount of money that you could ever possibly think of. So salary, how much money you make, would be a continuous variable. but it's not necessarily something that has to be measured. But most of the time, continuous variables are things like weight, height, and time, or age, things that can be measured by some kind of tool. It's not necessarily a physical tool that you take out of your pocket and measure like height. Age and time, those are really saying the same thing. Those could be measured with a calendar or a clock or a watch, those kinds of things. So we want to be able to classify quantitative variables based on, are they discrete or continuous variables? So this little graphic here does a good kind of job breaking this up. And again, we're going to get into nominal and ordinal here in a bit. But for now, all data can be classified as qualitative or quantitative, and then each one can be broken up a little bit further. So when we go out and record numeric data, there are two ways that we can write numbers. We can measure numbers or we can record numbers. Now, we want to record data in the nicest and easiest way for us to work with it. But just because I write down a data value does not mean that was the actual value that was written, because with continuous variables, decimal places go on forever. So values that must be rounded because of the limits of the measuring device, we always want to make sure that we present our data in the nicest and easiest way possible for us, given the restrictions for certain situations. So for example, heights might be rounded to the nearest inch. It would be easier just to walk up and look at a data set and say 72 inches, 73 inches. But not everyone is a whole inch when you measure their height. There are decimals, values in between all of those. And if we keep getting finer and finer with our measurements, you're going to get more accurate results, but it's going to make it more difficult when you're working with some whole numbers, some values that go 4 decimal places, others go 2 or 3. So we like to be consistent. Whatever method for recording your values you're going to use, you want to use that throughout the whole data set. But every once in a while, you would want to go back and look at the measured data. So what we do is we take a recorded value and then we break that up into intervals of possible measured values that could have been rounded to this recorded value. So here are some examples. So you could have a variable of length. The recorded value could have been 15 centimeters, but that actually could have meant that any value measured between 14.5 and 15.5 would have been rounded to 15. So if I measured a length of 14.8, that falls in this range, and using our basic rounding rule, that would round up to 15 centimeters. So here are a couple other examples. Temperature, if I record 86 degrees Fahrenheit, then the range for the boundaries of all values that would get rounded or recorded at 86 would fall 85.5 to 86.5. So there's a couple other examples here that you guys can look at, but I want to try one with you. So suppose I'm collecting data on people's weight, and my research assistant recorded a data value of 145 pounds. So the way this works is I'm going to take my recorded value, and if I want to come up with the boundaries for it, wherever this value stops, whatever the last digit place is, so whether it's digits, tens, or if it was a decimal place, whatever that last spot is, you're going to put a 0 in the next decimal spot. So in this case, because it's a whole number, I'm going to add a 0.0 to the end. If I was working with 0.43, then I would just put a 0 after that and make it 0.430. Wherever you've put that 0, then you're going to go 5 below and 5 above in that decimal place. So if I were to take this new version of this number and starting in this decimal place, go 5 below that, then that would actually take me down to 144.5. And then in that same decimal place, I go 5 above. That gives me an upper boundary of 145.5. So now I have my range. Any value that is measured and falls between these two would get rounded to my original recorded value of 145. So you guys can see or go back and look at the list here and see how they come up with these other boundary ranges for the time and the mass. So again, it's just a matter of putting a 0 at the very end, and then in that same spot going 5 below and 5 above. So 5 below 0.430 would be 0.425. 5 above would take me to 0.435. All right. So for now, categorical data. So qualitative variables collect information that falls into distinct categories. So what kind of category it is depends on what level of measurement we're working with. So not all categories are the same kind of data. It just depends on whether it's nominal or ordinal data. So the nominal level of measurement classifies data into mutually exclusive. So that phrase you're going to hear uh, every so often throughout the course, but it means they don't overlap. So categories that are distinct, they don't overlap. So no one could fall into two categories at the same time. So mutually exclusive, exhausting categories. Exhausting categories means there's no one that doesn't fall in one of the choices. So everyone should be able to pick one of the categories that are listed. And the big takeaway here, nominal data, it means there's no order or ranking that can be imposed on the categories themselves. So we don't use personal opinions. No one say, if I ask you what your favorite baseball team is, that's nominal data because there are no overlapping categories. Everyone should be able to pick one, and you can't ever rank whose baseball team is better. The only way that you possibly could come up with a ranking is if you used your own personal opinion to say, "Oh, I think the Orioles are better than the Yankees." That's not statistically supported. That's just personal opinion. Okay, so the whole idea is before you collect data, you can't use well, this one's more popular, so I'm going to rank that category ahead of time. This when we classify data, we're talking about just the options for the variables before actual responses have been collected. So, favorite baseball team would be nominal level of measurement. Ordinal level of measurement still classifies data into these mutually exclusive categories, but now they can be ranked. The big idea, though, is there's a natural ranking to them, but there's not a numerical reasoning for why one category is how much better than the other. So, some examples here. So, nominal level data. So, there's that zip code one. Remember, I said earlier, zip code is categorical because even though it's a number, it refers to a geographic location. No one can make an argument that one person's zip code is better than another. If you did, you would sound crazy. Gender, eye color, political affiliation, religious affiliation. All of these things would just be someone checking a box that they fall into. Um, and there's no way for us to decide, except for personal opinion, which again doesn't count, but there's no way for us to say this category should go before this other one. But for ordinal data, now I'm still picking a category that I fall into, whether it's by preference or just natural placement. I'm still choosing a category, but now there is some kind of order. It's not always necessarily better or worse, but there is some kind of order to these categories. So if I were to give you a letter grade on something, if I just say that your work was A quality work, then obviously, just from what we know about the way grades work, an A is better than a B. But there is no numerical way of me saying your work is 5 points or 10 points better. If that were the case, then I'd have to use numeric grades and not just simply letter grades. Judging first place, second place in some kind of contest. I know first place is better than second place, but just because I got first place for my art project and somebody else got second place doesn't mean that there is a numeric reason. Well, your painting was 5% better than the second place painting. There's no numeric explanation. So that's what it means by saying precise differences. So if there's some kind of natural ordering to the categories, it is ordinal level data. So let's try one. So here over on the right, I have some data that was collected, and it's listing different industries for transportation. And then it's also listing the number of injuries that occurred in a given span of time in each of these industries. So we're just going to go through and answer some questions about some of the vocab that we've looked at so far. So first off, we want to know what are the variables under study, and then we're going to categorize each as quantitative or qualitative. So in this case, there's actually two variables that we're studying. The first one would be industry. So what transportation industry am I looking at? And then the other one would be my number of injuries. So if we're classifying each one of these, industry is just a category. So in this case, our industry will be qualitative, but then the injuries, the number of injuries that are occurring, naturally that's a number. And it's not like the zip code. This is a real legit number. So this is a quantitative variable. So now for the quantitative one, so just for injuries, we want to categorize it as being discrete or continuous. So remember these two choices, the main qualifying factor is it something that has to be counted because it's whole number of occurrences, or is it something that could be measured and possibly produce decimal values? So in this case, for number of injuries, no one can take out a measuring device and measure the number of injuries. It's something that is counted, and you can't have half or three quarters of an injury. You either break your leg or you don't. You either lose a finger or you don't. So in this case, the quantitative variable being used here is going to be discrete. Okay, again, you can't have half of an injury. All right, now for our qualitative variable industry, now we want to think about the level of measurement. So that means, is it nominal or ordinal? So remember, can I order these categories, not based off of a pairing with another variable? So just looking at the names of these categories, is there any kind of natural order or sequence that they belong to? And in this case, with industry, there is no order. So in this case, this is just a nominal level of measurement. You can't rank or order the industry on its own. If we paired it with the number of injuries, then that's a different situation. That's not what we're doing here. So number 4 says the railroad is shown as having the fewest number of injuries. Does this mean that railroads are the safest form of transportation? So one really important thing about statistics is how we use the data that we collect. And a lot of times in statistics, data gets misused or misinterpreted. And sometimes it's deliberate, sometimes it's just because they don't know what they're doing with it. So you have to be very careful. You can't just take data on its own and make big extrapolations from it without thinking it through. So in this case, looking at it, it does look like railroad has the fewest number of injuries, but that does not naturally imply that railroads must be the safest form of transportation. So in this case, that could be true, but we just don't have enough information to make that kind of conclusion. And a lot of times in statistics, that's your answer. It's not necessarily going to be true. And you have to be careful of jumping to conclusions without having all the data necessary to back that conclusion up. So in this case, of all those given modes of transportation, railroad, bus, subway, trucking, or airline, railroads are probably one of the less frequently used modes, especially in our area. There aren't too many passenger car trains out there for us just to hop on and take somewhere. So because of that, if there's less people using that industry, then there probably are going to tend to be fewer injuries. And on the flip side, if you think about it at the top of this list, the airline industry has the highest number of injuries, and it looks like it's the most dangerous. But we couldn't jump to that conclusion either, because out of all of those options, airline is one of the most frequently used things. There's more customers, more workers involved in that industry, so more opportunities for injury. So just based on the data that we have, this would be a unfair conclusion to jump to. It could be one that you might see in the news and you might see someone making incorrectly, but we're not going to do that. 5 says, what factors other than safety influence a person's choice of transportation? So there are a bunch of different answers here, but this would be another kind of background information that we would want to think about if we really wanted to take this information and accurately portray it or use it to convince somebody of something. So in this case, lots of different things could go here. Location, so where are you in relation to where you're traveling to? I'm not going to take an airplane from Thurmont to Frederick. I'm not going to take a railroad from Thurmont to Alaska. That would take forever. So it's just a matter of distance that you're traveling, how far you are from the nearest railroad. I don't know where the nearest passenger car train would be for me to even access. How much it costs. If you don't want to spend a ton of money, you might be looking for a cheaper option. The weather, probably not a good idea to take an airplane somewhere when it's storming out really badly. There's lots of different things that could influence a person's choice of transportation besides just the safety. All right, and then for the last one, from the information given, we want to comment on the relationship between the variables. So again, this is where you want to be very particular about what you say. Sometimes when you're commenting on the relationship that you see in data sets, you're not going to be coming up with an earth-shattering conclusion that nobody saw coming. It's okay to be bland and boring when you're reporting on data. The main idea is you're saving someone the time of having to go out and collect the data. Even if it's something very straightforward, you still are doing what you're supposed to. So we don't want to make the mistake and do something like was stated in number 4. So realistically, the only thing that we can comment here is, based on the data alone, railroads have the least number of injuries and airlines have the most. We can give possible reasons for why that is, but you don't want to be definitive in those statements. We don't want to say this is definitely due to this, but we can make some conjectures. So this may be due to the high volume of workers and customers involved in the airline industry versus the much lower number of workers and customers in railroad. All right, so now we're going to talk about how we collect data. So we know how to classify it once we set up what we were looking for, but how we collect data is important. So data can be collected in a variety of ways. One of the most common methods is through the use of surveys. So 3 of the most common methods are the telephone survey, mailed questionnaire, and the personal interview. Once a statistician decides on a method of data collection, so whether you want to call people, mail out a questionnaire, or just talk to them face to face, most people, when they're collecting data, most statisticians are going to be using a personal interview, doing it face to face. But occasionally, you could do it over the telephone or mailed questionnaire. We can do digital surveys now as well. But once we've decided on that, now we have to identify how we're going to get our sample, or if we're lucky, a population. So if the statistician is fortunate enough to be able to collect data from everyone in the population, then rather than calling that a survey, they're actually conducting a census. Like we talked about earlier on in the video, census is everyone in the population. And most of the time, if you're collecting data that is going to be meaningful, your population is going to be way too large for that to happen. So we're going to have to rely on being able to collect a sample. So to do that, we need to know the 4 major ways of collecting samples. So researchers use samples to collect their data about a variable from a large population because in most situations, it would be extremely costly and time-consuming to collect data from everyone. Using samples saves time and money, and in some cases enables the researcher to get more detailed information about a particular subject. The selection of samples must be done carefully, however. If the researcher is not careful in selecting their subject, they may accidentally, or in some cases, intentionally create some type of bias. Oftentimes, a researcher can have a negative influence on the accuracy of the results. Bias is the result of some kind of influence on the results of a study caused by the researcher, whether it's intentional or not. So if you, as the researcher, input some kind of influence, then your data is automatically corrupted and we can't necessarily trust it. It's the goal of every statistician to never create any kind of bias. There are certain things as a researcher we can do to help prevent those sources of bias. Some situations, bias is inherent and you can try as best as you can, but there's still going to be some kind of influence. It really just depends on what kind of information or data you are trying to collect. To create a sample that is unbiased, the researcher must select a sample where each member of the population has an equally likely chance of being selected. And there's 4 basic types of sampling methods. So we're going to take a look at each one here. So the first kind is random sampling. So for something to be random, it's selected by using chance method or random numbers assigned to members of the population. Let's say that we have a population of 85 subjects and we want to choose a random sample of 15 of those subjects. So your calculator actually has the ability to randomly generate numbers. Now, it's not completely random, but it's as close as we can get with computers. So the idea is in your calculator, you're going to go to the math button. Then we're going to go over to the left, and it shoots us out to back to the end under probability, and we're going to go to option number 5 that says rand int. So you have to tell the calculator 3 values: smallest number to choose from, largest number to choose from, and then the number of random integers to be selected. And then you use arrows to scroll through. So these are kind of the screen grabs of what it would look like. So when we get to this point right here, what you're telling the calculator is you want it to pick 15 random numbers between 0 and 85. So everyone in the population is given a number, and every one of these numbers that's listed then represent or correspond to someone in your population being selected. So if it's truly randomized, the idea is we're just scattering through our population and randomly picking people out of it. So to truly be random, the idea is that every person in the population should have the same fair and equal chance of being selected, and every different possible sample should have the same probability of being selected. So basically, the key word is fair. Everybody should have a fair shot at getting picked to be in that sample. So that's our first method. The second kind is a systematic sampling technique. So this is obtained by numbering each member of the population. We then choose a random starting point on the list of subjects and then select every nth subject. And we continue until we have enough people to fill out our desired sample size. So for example, suppose there were 2,000 kids in a high school and you want to collect data on the study habits of those students. To do this, you want to select a sample of 50 students. So since 2,000 divided by 50 equals 40, then n equals 40. So we're going to pick every 40th member of the population. To do this fairly, though, it wouldn't be fair if we just started with the very first kid on the list and then chose every 40th kid, because if you're not that first kid or the 41st or the 81st, then you didn't have any chance whatsoever of getting in that sample, because I was always going to start with the first kid on the list. That's why we have to randomly choose a starting point. When we do that, now everyone still has that fair chance of getting chosen. But how we move from one person being picked to the next is no longer random. It's systematic. That's the general idea. So let's say that if we randomly chose the 12th person for us to start with, then I would just move 40 down the list each time. So person number 12 would get picked, person 52, 92, 132, and so on. That's the general idea of systematic. So we pick a random starting place, and then we're moving the same number of people each time. That's the idea here. You typically see systematic sampling in manufacturing and factories. Anytime someone's doing quality control, it's hard for a human on a conveyor belt looking at objects to just randomly choose items off the belt to check. Instead, they'll pick a random starting spot in the morning, and then they're going to check every 5th or every 10th or however many they need to fill out their sample. So that's the general idea of systematic. Stratified sampling is hands down the best, but there are issues with it. If we can do it, it's always going to be the best one. So we first split the population into subgroups called strata, and those strata are based on some characteristic that may have a serious effect on the variable that we're studying. Once they're divided into strata, the statistician randomly chooses members from each different strata. All of these subjects are combined to create the sample. So for example, suppose there were those 2,000 kids in a high school and we want to collect study habit data. One outside factor that may affect study habits would be what grade the student was in. Hopefully, seniors have better study habits, or at least more refined study habits than freshmen, because they've already been through 3 years of high school. So what grade you're in could have a direct influence on your study habits. So if we didn't use that information to help us collect data and collect a better sample, if we just used a random or a systematic sample in this situation, there's always a possibility that I could end up with all freshmen or all seniors in my sample, and that might have a big influence. So using the stratified sampling method, we could group the students by grade to start, and then we randomly select a number of students from each grade. So again, if we think about why that would be better than systematic or rambling, that's that general idea. If I were to use systematic or rambling, we're trying to identify some possible sources of bias or non-representative results, and we use those to create the strata. If we do that ahead of time, before we actually pick our sample, that's what allows us to eliminate that bias. But if we were to use a systematic or purely random sample, there is still that chance that everyone we ended up picking, or a majority of them, end up coming from one grade. And because we're saying that kids in the different grades should all have similar study habits, that would not be a good representation of the whole population. So if I got all freshmen, odds are they're not going to have great study habits. And if I use that to represent everybody in the school, now I would say all 2,000 kids have bad study habits. And that might not be true. It might just be true about the freshmen that we sampled. So that's stratified. Again, it's a much better sampling technique, but it's a little harder, more time consuming to set up. And then our last one, cluster sampling. So in this case, the researcher divides the population into subgroups called clusters based on some characteristics. So that sounds pretty familiar. That sounds similar to stratified. The big difference, though, between stratified and clustered samples is that with cluster sampling, the subgroups are typically pre-existing or natural groups. They're not always, but a lot of times they are. But then another big difference is once the entire population is put into those clusters, the researcher will randomly choose entire clusters. So sometimes it would be one whole cluster. If there are 50 subgroups or clusters to start with, then I might randomly choose 3, 4, 5 of all of those clusters to make up my sample. So once a cluster is selected, everybody that was in that subgroup all join together to make up my sample group. So this is similar to stratified, but stratified was make the subgroups and randomly select a few from each so that all the different subgroups are represented. Cluster sampling, instead of having to go around to all of the subgroups, I just have to pick a couple of them and use everybody in those for my sample. So for example, suppose a researcher wishes to survey apartment dwellers in a large city. If there are 10 apartment buildings in the city, the researcher can select at random 2 of the buildings. So in this case, my clusters are the different apartment buildings, and they're already all the people already live in them. So I don't have to divvy up the groups myself. They're naturally existing groups. And I'm going to randomly select 2 of them, and everyone that lives in those 2 buildings, all of them go together to create my sample. So if I wanted to do this same study but with stratified sampling, I could still use the 10 apartment buildings as my strata, but to make it stratified, then I would have to randomly sample a few people that live in each of the 10 buildings. So stratified, a few from each, or cluster, everybody from a few of the subgroups. So it kind of flips around there. So there's one other method of collecting data. It doesn't fall under the realm of our 4 main ones, but it is one that's often used. We may use it at different points throughout the course this semester, but it's called convenience sampling, and it's kind of exactly what it sounds like. The first 4 methods all have their pros and cons, but they're all based around some kind of randomized randomized collection process. We're using some method of randomness. But for convenience sampling, it's really a matter of getting data from people that are convenient. So the researcher simply chooses a sample using the most convenient sample possible. So the closest people you have access to, we get data from. This is not a reliable method of sampling and will almost always produce some kind of biased results because oftentimes the people you have easiest access to are going to have very similar traits. And if any of those traits relate to what you're collecting data on, it can definitely mess up your results and produce unrepresentative results. So when possible, we always want to try to use one of the 4 sampling techniques. So we got to be really careful. For example, a researcher wanting to know about the shopping patterns of mall visitors could choose a convenience sample just by asking people as they walk into the mall. So if you're just asking people that come in, there's nothing random about that. Now, if you chose a random number to start with, say I randomly chose 7, if I start with the 7th person that walks into the mall in the morning, and then I ask every 10th person after that, now I've employed a systematic sampling technique, and I've introduced that randomness at the beginning, so everyone still has a fair or had a fair chance to be selected. But simply asking people as they come in, there's nothing random involved, so the results aren't going to be truly representative. All right, so once we determine our sampling technique, then we can talk about what kind of thing am I going to do to get the data. So what kind of study am I going to uh, use? And the first kind that we could use is called an observational study. So this is one of two types of studies that a researcher can conduct. In an observational study, the researcher merely observes what is happening or what has happened in the past and tries to draw conclusions based on these observations. So, for example, data from the Motorcycle Industry Council stated that motorcycle owners are getting older and richer. Data were collected on the ages and incomes of motorcycle owners for the years 1980 and 1998 and then compared. The findings showed considerable differences in the ages and incomes of motorcycle owners for the 2 years. In this study, the researcher merely observed what had happened to the motorcycle owners over a period of time. There's no type of research intervention. So again, the idea here is you didn't go out and make people do something different than they normally do. You just looked back at what has already occurred and you gathered data and compared. Sports analysts do this all the time. Collection of sports stats, and we just simply explain what is going on. That's all we're doing. An observational study is you're just merely observing and then reporting what you saw. The opposite of that is an experimental study. So the second type of study a researcher can conduct in an experimental study, the researcher manipulates one of the variables in the study and tries to determine how the manipulation influences other variables. So that's the big key. We're going to change something about what someone does in a typical day, and then we're going to see, does that change influence some other variable's results in the way that I expect it to? Sometimes it won't, sometimes it will. In a true experimental study, subjects are randomly assigned to a group. So there's typically more than one group of subjects in an experimental study. Sometimes random assignment's not possible, so researchers will just simply use pre-existing groups. That's called a quasi-experimental study. It's used quite often in educational studies simply because kids are already in classrooms or schools or counties or school districts. So sometimes it's easier just to use pre-existing groups rather than making up brand new groups through random assignment. So for example, a study conducted at Virginia Polytechnic Institute and presented in Psychology Today divided female undergrads into two groups and had the students perform as many sit-ups as possible in 90 seconds. The first group was told only to do your best, while the second group was told to try to increase the actual number of sit-ups done each day by 10%. After 4 days, the subjects in the group who were given the vague instructions to do your best averaged 43 sit-ups, while the group that was given the more specific instructions to increase the number of sit-ups by 10% averaged 56 sit-ups by the last day's session. The conclusion then was that athletes who were given specific goals performed better than those who were not given any specific goals. So you can see a clear difference in this setup than what we looked at with the observational study. So in this case, you're changing something about the natural existing thing that someone is going to do. You're influencing the results in some way. And that's the idea. We're taking a manipulation and seeing if that has an effect on the end result. So every experiment has inherent independent and dependent variables. You guys need to know what those are. So in an experimental study, this is for the independent variable, this is the variable that is being manipulated by the researcher. It's also called the explanatory variable. So in the sit-ups example, we want to know what was the independent variable. So if you think about what was manipulated by the researcher, that would have to be the instructions. So the independent variable were the directions given to each student. So when we split them up into the two groups, One group were told just do your best, so that's not really anything special. But then the other group were given directions to set a goal of increasing by a specific amount each day. So in that case, that would be the manipulation. So that's our independent variable. The dependent variable is the outcome that is studied to see if it has changed significantly due to the manipulation of the independent variable. So it's the end result one. So we're trying to see if the manipulation done to the independent variable has some kind of effect on the dependent variable. So sometimes it's also referred to as the outcome variable, or another name for it is the response variable, because it responds, its value responds to the manipulation oftentimes. So in the sit-ups example, if you think about what the dependent variable is, or what the end result is that we're comparing, that would have to be the number of sit-ups that the student could do. So that's our idea. We made a manipulation in the independent variable, or the directions the kids got, in hopes that we saw a different number of sit-ups between those two groups. So that's our independent and dependent variables. So in order to create an experiment, it's important to identify what you want your independent and dependent variables to be, but then we also need to identify which subjects will be in which group. So whenever we do an experiment, we have to have different kinds of results to make comparisons. That's how we can tell if our manipulation actually worked or had any kind of influence on that dependent variable. So there are two groups, or at least two groups. Some studies actually have a lot more than that. One group is called a treatment group, and that's the group that will receive the manipulation. Some studies, there's going to be more than one treatment group. If you have more than one specific kind of manipulation, you can have 2, 3, 4, 5. There's no limit on how many treatment groups you can actually end up having. A control group is the group that will be completely unaffected by the research. So you've probably heard that before, having a control in an experiment. It's a way of getting some baseline data so that we can have something to compare the treatment group results to. So it's the comparison of the data collected from the treatment and control groups that determines if the manipulation actually has an effect on the results or not. So that's where we get our comparison. So some disadvantage when we create an experiment. So there's several major disadvantages to conducting an experimental study. One of those is the Hawthorne effect. So you may have heard of this in a psych class if you guys have taken psychology, but the Hawthorne effect says that when subjects know that they are participating in an experiment, they can actually change their behavior in ways that affected the results of the study. So if I ask for volunteers to be a part of a weight loss experiment, and I say, here's a pill, take this for a month, and come back and we'll measure your weight. As soon as you know that you're a part of an experiment, if you know that your weight's going to be measured at the end of the study, you may subconsciously or sometimes consciously make decisions and change things about your behavior that you wouldn't have done had you not been a part of the study. If I immediately tell you that I'm going to measure your weight in a month, you might start exercising your butt off when beforehand you never would have. So that's the Hawthorne effect. It's not like a widespread issue. It's not like everyone's going to change their behavior in the exact same way. So it's just something that we have to be on the lookout for. Sometimes you may have individual suspicious results, things that seem way out of the ordinary or out of the ordinary for that particular group, treatment or control. And so those would be situations where we may have to investigate, well, did you change anything about your behavior during the process? And those kind of values may have to be removed from the study because they don't fit in with everyone else. A confounding variable is one that influences the dependent variable but was not separated from the independent variable in the first place. So if you think back to the sit-ups example, so sit-ups has to do with physicality and being in good shape. And if someone wanted to do better, or if someone was having their number of push-ups, or excuse me, sit-ups measured, one possible confounding variable would maybe be diet. Maybe someone started to eat better during that process, and that left them in a better position to increase the number of sit-ups that they could do throughout the process of the experiment. So something like that, diet in this case, would be a confounding variable because it could influence the results of the dependent variable, but it wasn't separated from the study. It was not used or identified beforehand. A lot of times, if you can identify confounding variables, we can actually use those to set up strata or subgroups in the treatment and controls and do what's called blocking to block for the influences that those particular variables can have on the results. And lastly, the placebo effect. Everyone's heard of this one. So the placebo effect is a very common side effect of someone being a part of any kind of study. The placebo effect is when a member of the control group in an experimental study actually shows significant results similar to what you would have expected had they been a part of the treatment group, despite only receiving the placebo. This happens a lot in drug studies for pharmaceutical companies. People will test out a new drug. Let's say that there's a new heart medication to lower blood pressure, and one group gets the new drug, another group gets the old drug. No one in the study actually knows which pill that they're receiving. That way we can try to eliminate some influence on the results. But some people, if I say, here's a pill and it's going to lower your blood pressure, even though it's a placebo drug, a sugar pill that shouldn't have any kind of effect on those results, some people actually can show signs that they would have only expected given the real medication. So it's a phenomenon in psychology, and it's a very common one. So it's just another thing to be on the lookout for when conducting an experiment. All right, so let's take a look at another example here and do some analysis. So this says, as the evidence on the adverse effects of cigarette smoke grew, people tried many different ways of quitting smoking. Some people tried chewing tobacco, or as it was called, smokeless tobacco. A small amount of tobacco was placed between the cheek and gum. Certain chemicals from the tobacco were absorbed into the bloodstream and gave the sensation of smoking cigarettes. This prompted studies on the adverse effects of smokeless tobacco. One study in particular used 40 university students as subjects. 20 were given smokeless tobacco to chew, and 20 were given a substance that looked and tasted like smokeless tobacco, but did not contain any of the harmful substances. The students were randomly assigned to one of the groups. The students' blood pressure and heart rate were measured before they started chewing, and 20 minutes after they had been chewing. A significant increase in heart rate occurred in the group that chewed the smokeless tobacco. So we're going to use this study and answer some questions here. So first off, we want to know, what type of study was this? Was this observational, where we just merely observe what's going on and then present the results? Was it a quasi-experimental study where people were in pre-existing groups and we used those and then set up our treatment and control, one of them getting each one? Or was it a straightforward experimental study where people were randomly assigned? So in this case, it's actually told to us that the students were randomly assigned to one of the two groups. So in this case, this is an experimental study. Next up, what are the independent and dependent variables? So remember, independent is the variable being manipulated somehow. Dependent are the results we're going to compare at the end. So in this case, our independent variable is whether the participant chewed tobacco or not. So that's what we manipulated as researchers at the beginning. We chose to place them in one of the two groups with the different directions. And then at the end, we compared the dependent variable of their blood pressure and heart rate. So that's the information that we're hoping is influenced by whether they receive the real stuff or the fake stuff. So in this case, we want to know which was the treatment group. So again, the treatment group is always the group that's doing something different from what they would have normally been doing. So in this case, our treatment group is the group that actually received the smokeless tobacco. The other group would be our placebo, or excuse me, our control group. So they actually received a placebo. So next up, could the students' blood pressures be affected by knowing that they are a part of the study? So if you really think about it, blood pressure kind of goes up and down when you feel stress or you get worried about stuff. So in this case, a student's blood pressure might not be affected by knowing that he or she was a part of the study. However, if the student's blood pressure were affected by this knowledge, if you really think about it, all the students in both groups, whether they had the real chewing tobacco or not, all of them probably would have been affected in a similar fashion. So this might be a simple example of the placebo effect. So that would be one thing that you would want to be worried about in that control group. So because the control group had the placebo, we wouldn't expect their heart rate and blood pressure to be affected by the fake stuff. But if they do feel that kind of worry or anxiety from being a part of the study, then they might actually show higher blood pressure and might be caused by the placebo effect. If we want to list some possible confounding variables, again, in this case, we're thinking of things that could affect someone's blood pressure or heart rate, but isn't controlled by our independent variable, and that's the kind of tobacco they're getting. So there's lots of different possible answers here. Just to list a few, really just think about anything that may affect the person's blood pressure or heart rate that's not a part of this study right now. So that could be their beginning weight. Heavier set people tend to have higher blood pressure than skinnier people. Their exercise habits, people who regularly exercise are going to have lower blood pressure typically. Their diet, if you eat a strict diet, a healthy diet, you're probably going to have better heart rate and blood pressure. If you're a regular drug or alcohol user, then both of those things directly affect a person's blood pressure and heart rate. So those are all things that if we're just getting 40 university subjects randomly, then we may not have accounted for all those different things ahead of time, or at least they didn't tell us that they did in this study. And then lastly, do you think this is a good way to study the effect of smokeless tobacco? So again, before we can generalize from a sample to everybody, we want to make sure, think about, did the sample that we used accurately reflect the larger group of people? So in this case, it's an okay study. They randomized, they got volunteers, they randomly assigned them, they have a treatment and control. But the problem is we can't really generalize the findings to everyone because it only used university age students. A 20-year-old that's in college is going to have a much different heart rate or blood pressure on average than a 65-year-old, someone who has been smoking or had an entire lifetime of possible health issues. So because we only used university age students, this would be a really hard study to generalize towards a population that includes a wide range of ages. So hopefully you guys have a general idea here of some of the basics around collecting data, analyzing what kind of variables, what kind of studies that we are conducting. So you guys are going to try a few problems to practice with this vocab now. And if you have any questions, please reach out.